let's finish this proof. So if we're careful, we can actually do this in a very short fashion. Let's find S of W1 plus W2. Okay, well, what's this defined to be? There is a unique x so that T of x equals W1 plus W2. And that's what that is. S of W1, W2 equals x when there is a unique x, and that's what that x is. X is the unique element so that T of x equals W1, W2. But also, now keep in mind, there's a unique x so that T of x equals W1 plus W2. But also, T of SW1 plus SW2, well, because T is linear, if I have another pencil, disaster. Okay, all is good. Lights back on, new pencil, and refocus the camera when everything went wrong at once. Okay, so what were we doing? Well, we were saying we want to show that S is linear, right? So I said, first, let's find S of W1 plus W2. Well, that's going to equal some x. Which x? Well, there's a unique x, so that T of x equals W1 plus W2, and that's the x. Okay? But also, T of this element happens to be equal to T of S of W1 plus T of S of W2. And we know that this is W1 plus W2. Remember, we know that T and S cancel each other out. We just don't know that S is linear. We know that T is linear and that T and S cancel each other out. Okay, so what happens here? I found another element that has the property that T of that element is W1 plus W2. But uniqueness, there can only be one. So what does that mean? It means that S of W1 plus W2, which is equal to x, it also has to be equal to this element, which also has the property that T of this equals W1 plus W2. So that gives me this, and I am good. That's what I wanted to show. Okay, now we want to do it for scalars as well. Okay, so I want to find S of lambda. Should I use I'll just use a single W. Okay, so what do I know? I know there is a unique x so that T of x is equal to lambda W, and that's what that's defined to be. It's defined to be the unique x, right? That's how we define S. But what else do I know? Well, I know that T of lambda of S of W, because T is linear, this is lambda of T of SW, and because T and S cancel each other out, remember, we know they cancel each other out, we just don't know that S is linear. So this ends up being lambda W. So, oh, look what we have here. I have that S So I have that S of lambda W is going to be equal to x. But I know that there is a unique x so that T of x equals lambda W. So since T of this equals lambda W, this must be equal to x. One more time, I'm using uniqueness. So this must be lambda S of W. And I am done. I have shown that S is linear as well. So that was a long proof because we had to go, we had a lot of different things to show. But we can put it all together now and say that T is invertible if and only if T is a bijection. So this is obviously for linear transformations here, because that's what we're discussing. So a linear transformation is invertible if and only if it is both injective and also surjective. And it's an if and only if, so as long as you have a bijection that happens to be a linear transformation, you know it has an inverse. And that completes this important proof.